big deal. I is a constant in this case. It's in the integram to cover all the cases when it's not constant. But for this, we're going to let this be a steady current, which is code word for doesn't change magnitude. So this could actually come out of the integral now. Let's do it. Let's do a little blackboard algebra. And we're just left with this. So now we have to figure out what all this stuff means. The R, I think, is going to be obvious. The R is just like it was in the electrical case, which we're probably going to express in this orientation at least. R is equal to x squared plus a squared square root, right? This is just Pythagorean theorem. So far, really, really similar to how we proceeded. Okay, now that handles the denominator. What about the numerator? Well, remember DL is our placeholder for the actual direction of integration. So, looking at this orientation, what do you think is going to be our actual direction of integration? X, Y, Z, theta? Probably X, right? So, in our specific case, let's just agree to let DL, and this is a vector, so I gotta be careful with that, be dx, which is not a vector. To make this a vector, I've got to put in an I hat. So all I'm doing is I'm taking this placeholder, DL, which is a vector itself, and turning it into a vector that I'm going to use, because I can just look at this and go, I'm going to integrate in the horizontal direction. I'm used to calling that x, call it x. But I can't just say dx because this is a vector itself. So to make my dx, which is a differential length, into a differential length vector, I just slap on the I hat, right? If I were doing this vertically, it'd be dy j hat. If I were doing it in the z direction, you see where we're going, right? So that's all. Now, what about the r hat? Well, if I draw that in, there's r hat. And what does the cross product tell me to do? Cross product, if you remember, says take the magnitude of this guy, multiply it by the magnitude of this guy. Why don't I write this down? Definition of the cross product. A cross B tells me take the magnitude of A, magnitude of B, times the sine of the angle between them, and then put in a unit vector that gives me a vector perpendicular to both of them. Okay. Oh man, I shouldn't be using A twice. That's a bad plan. Let me just make this a capital A. That should be cause the least amount of consternation. All right, there we go. Yep. So this is a capital A. Sorry. Not the same thing. Okay. Well, let's put all this together. Let's do a little side work. So, if I'm going to do DL cross R hat by that definition, this is going to be magnitude of DL, magnitude of R hat, times the sine of the angle between them, times this normal hat. Okay. Well, I've already expressed DL a little bit differently. That's going to be magnitude dx I hat times magnitude r hat, sine of the angle between them, in hat. Now, dx is never going to be negative. It's not a thing. It's also not. The reason the absolute value there is to get rid of the vector and make it a scalar. Dx is already a scalar, so it's okay if I do this, bring it outside the modulus, right? And then what I'm left with is I hat, I should say magnitude I hat, magnitude r hat, sine of theta in hat. All right. Questions on why I did what I did? Anybody? Because this is pretty critical to see what we're doing here. It won't always be this exact process because we have other geometries, but this is the exact idea. I express my DL in terms of what I'm going to actually be integrating over. Anybody, did I lose anybody? All right, well now it's somewhat easy. What is the magnitude of I hat? 1. What's the magnitude of R hat? 1. You see the advantage of expressing it in terms of unit vectors, right? They just go away. And then what I'm left with is dx, which is good. That's my integration variable. And then sine theta, and then this n hat. So after I run the cross product, I have dx sine theta, and then this n hat, which we got to figure out what n hat is, right? All right. Well, what is theta? First of all, remember theta is a vector that runs from the first component of your cross product to the second one in counterclockwise direction. So what is my? I didn't draw it. There is dl right there. So theta, by the definition of this, is right here. The sine of that angle is what I need. And just like I did with electricity, I'm going to express it in terms of my physical parameters, right? So just looking at it, sine theta is equal to opposite over hypotenuse. That's A over R, where R is x squared plus a squared square root, right? So also really similar to how I did this in electricity. And then that gets put into my integral. So are we okay with that? Okay. So I need to erase some stuff. You guys all have this stuff down here. Speak now for everyone. All right. It's pretty egregious, actually. It's easily fixable, but it's pretty egregious. Anybody see what I did? I don't know. It's right. That's right. My brain is going to a strange place. It happens routinely, as you probably noticed by this point. Yes, this is correct. Okay, this is correct. Okay, never mind. We're good. One moment of panic, but I'm good. Okay. So, what am I left with in my integral? U naught I over 4 pi times this integral, which in this case is running from A to B. And then I've replaced the dl across R with, I think I erased it. What did I have here? I did erase it. Dx, and then sine of theta, A over x squared plus a squared square root. And this itself is over r squared, which is x squared plus a squared. And so what I have in the integrand, let's just put these together. And that's something which we've seen before. Now, what I haven't done is that n hat. Okay. So here's where we're going to be a little tricky. Because what I've asked you for is the electric field at this one point due to this line. Now, unit vectors are there to show you direction, but unit vectors are not all constant, right? X hat is constant. I should say I hat. I prefer X hat, but I hat works. I hat is constant. J hat is constant. Z hat is constant. But in other geometries, you get other unit vectors like a theta hat, right? You can think of a tangential coordinate system. Theta points tangentially to a circle, right? Theta hat tells you the magnitude never changes, but the direction absolutely does. So that actually becomes very difficult to integrate if your unit vector is changing. And we're going to find that something like that will happen here, but our trick is in this position, just at that one point, right? N hat is not changing because I'm only looking at one point. If that makes any sense. Okay, it's a unit vector mutually perpendicular to both of those vectors. To get it, we're going to use our right-hand rule that we learned last time. We looked at it in the context of forces. Right-hand rule works for all cross products, right? So what is it? Put your fingers in the direction of the first vector. That's DL right here. Curl them into the direction of the second vector. That's R hat right here. Stick out your thumb. Now I don't have any charges to check. This is not a force thing, it's just a cross product thing. So that's the direction. Out of the board. So N hat looks like this. We're not going to call it N hat, that's just a placeholder. We're probably going to call it that K hat. Everybody see that? Okay. Now, one more thing before we take our exam. That's in one position. So let me redraw this system as if I'm looking down the wire. So here's my wire. All right. Here's my wire. And the current is coming out of the board at me. If I can flip around my perspective, what I've found is that at this position, right above it, at some distance A from this thing, the field looks like that. Right? So let me ask you this. If I were to rotate this perspective, right? If I were to just take this wire and rotate it this way, and so that this point moves over to this point, what would that look like? It would still be perpendicular. So that would look like this. Let me throw chalk around. Let me rotate it again to this point, still perpendicular. Looks like that. This point, like that. This point, like that. And you see what's happening? It's a circle, right? I just looked at it at one point, but then if I think about it, and I shift my perspective, what this does is it forms a circle. The magnetic field line actually does this. Remember what the field line is. It's not a vector itself, but it's a collection of vectors. What I'm doing is I'm finding each individual vector. So the field line forms a circle around this long straight wire. So in this position, it's just fine to say K hat. But really, if I need all positions, I'm going to call that theta hat, where theta is the vector, is the angle, right? Theta hat is this unit vector. All right, we're going to do a lot more with that next week. I'm going to send you some videos that I would really like you to watch before then. Now, let's take an exam. And after class, if you have any questions, feel free to ask them.
So if you have that wire, you put your hand like on the wire, and your thumb points in the direction of the curve. Whatever way your throw, the way it turns.
Pass one down. So you can go ahead and get it.